everyone, welcome to the 7th grade math statistics notes, where we are focusing on random sampling and comparing populations. Let's get started with vocabulary. We're going to define words here and get into them more as we go through the notes. Statistics is the science of collecting and organizing data. Population is the entire group with which you want to draw conclusions. Representative sample is a subset or like a smaller group of the population that represents the characteristics of the population. Random sample is when each member of the population has an equal chance of being chosen to be part of the representative sample. Inferences are conclusions drawn based on the data. Now we're going to talk about measures of center and measures of variation. Again, we're going to define them and get into them a little bit more as we go through the notes. Measures of center are values of data that describe the center position of the data. There are a couple of different ways to measure the center of data. We talk about the mean, median, and the mode. First of all, the mean is the sum of all values divided by the total number of values. The mean is often referred to as the arithmetic mean or often called the average as well. The median is the middle number when numbers are placed in ascending order. Lastly, the mode is the number or numbers that are repeated most often. Now let's talk about measures of variation. Measures of variation are values that describe how much the data is spread out. There are various measures of variation, but we are going to talk about the range, the interquartile range, and the mean absolute deviation. The range is the difference between the largest value and the smallest value. The interquartile range is the difference between quartile 3 and quartile 1 in a box plot. Quartile 1 through quartile 3 will contain the middle 50% of the data. Mean absolute deviation is the average distance that each data point is from the mean. We're going to get into a little more depth on what is population. First of all, the purpose of statistics is to use a limited sample to make valid predictions about an entire population. When thinking about a statistical question, you need to define your population or the entire group with which your question refers to. For example, let's say you would like to determine how many students in your school own a cell phone. The population would be all the students at your school. How many boys at the local high school have a job? The population would be all the boys at the local high school. So just a quick review, population is the entire group with which your question refers to. So let's see if we can determine the population of some questions. So if my question is, how many people in the United States aged 18 and older voted in the last presidential election? So I'm thinking about my entire group that it's referring to. In this case, it's people in the United States age 18 and older. How many women over the age of 25 in England still have at least one of their wisdom teeth? So in this case, my group would be all women over 25 in England. Okay, now we're going to talk about representative samples. Let's think about surveying an entire population. That is usually very difficult. Like for me to survey every single person in the United States that is age 18 or over would be very difficult. So we use representative samples. Representative samples are a subset of the population that represents the characteristics of the population. Going back to the question about women in England over 25 who have their wisdom teeth, the population is the women in England over 25. To ask every single woman in England over 25 about their wisdom teeth is going to be very, very difficult. So I'm going to get a smaller group but they still need to be women, they still need to be in England, and they still need to be over 25. Let's say you want to know how many boys at your local high school have a job. Would collecting data from the boys and girls in the high school give a representative sample? Why or why not? Well, my entire population would be boys at the high school. So if I'm getting data from boys and girls in the high school, that's not going to be a representative sample because it doesn't have the same characteristics as the population, because the big population shouldn't include the girls. It's just the boys. What if you asked all the boys that went to the grocery store in town? So if I went to the grocery store and I asked all the boys there about them having a job, would this be a representative sample? Why or why not? Remember, my question is I want to know how many boys at the local high school have a job. So if I'm going to the grocery store and asking boys, does that represent my population? And again, no, because not all the boys at the grocery store attend the local high school. What about if I collected data from the boys in the school cafeteria? So if I went to the high school and I went to the cafeteria and I asked the boys if they had a job, could this give us a representative sample? And the answer there is yes, because all the boys in the cafeteria are going to be attending the school as well. On the next page, we're going to get into random samples. Blank the correct population tends to produce representative samples. So right there, we're going to write random sampling. So once I identify the characteristics of my representative sample, I still need to figure out how I'm going to get my representative sample, and that's when we use what's called random sampling. A random sample is every member of the population has an equal chance of being chosen to be part of the representative sample. The key to this is every member of the population has an equal chance of being chosen. Let's go back to the question of how many students in your high school own a cell phone. Look at the sampling methods below and explain whether they would or would not produce a random sample. So my question is, how many students in your high school own a cell phone? The population is all students at your school. So let's say there's 1,500 students and all of them would be part of the population. For me to ask every single one of them might be difficult. So I'm going to get a representative sample. Let's look at this option. If I ask 20 of my friends if they own a cell phone, is that random sampling? Does every member of the population have an equal chance of being chosen? Well, if I just ask 20 of my friends, then no, because everyone who is not your friend does not have a chance of being chosen. Let's look at option 2. Stand at the entrance of the school and ask every 10th student that enters in the morning. Yeah, that's more likely to produce a random sample, since every student has an equal chance of being chosen. Let's look at option 3. Ask all the girls in your school. In that case, again, no, because the boys do not have a chance of being chosen. Option 4. Assign each student in your school a number and use a random number generator to choose 200 students. Again, yes, that would work because every student has an equal chance of being chosen. Okay, next page we're going to talk about inferences. A truly representative sample supports valid inferences of a population. Inferences are conclusions drawn based on the data. Inferences are often used to make predictions about a population. This is one of the main uses of statistics and sampling, is to learn about a population and make inferences. Sally and Sean are both running for school president. You are curious which one is going to win. You create a random sample to ask the students which one they will vote for. You survey 100 out of the 200 students in your school. 73% of your representative sample said they were going to vote for Sally, and 27% said they were going to vote for Sean. Therefore, you can infer or kind of predict that Sally will become the school president. So as long as you made the sample representative and random, then this could be a pretty accurate prediction. Generating multiple samples of the same size can help you understand how your predictions vary. So sometimes I'm going to take a whole bunch of different representative samples and get a whole bunch of data and then compare the data to see how it varies. You would like to determine the average word length in the novel you are reading. So the population would be all the words in your book. So for me to go and count every single word in my book and how many letters it has would be impossible. If it's a longer book. So I'm going to create a method to create a representative sample. So a method to random sample my books might be from one hat pull out a page number and from another hat pull out a number that indicates which word on that page should be part of your representative sample. So maybe if I pick out a number 8, so page 8, and I pick out the number 20, that means the 20th word on that page. And that would work because every word would have an equal opportunity of being chosen to be part of this sample. Now, you may have a different idea how to create a representative sample, and as long as it's representative and random, meaning every word has an equal opportunity of being chosen, then that will work. Let's talk a little bit about comparing populations. Comparing populations is also a very beneficial tool in statistics. When comparing populations, we are specifically going to compare a measure of center and a measure of variability. And we talked a little bit about the measure of center is just about the center of the data, and the measure of variability, we'll talk more about how the data is spread out. The 3 measures of central tendency that we are going to talk about are the mean, median, and mode. 3 measures of variability, or how much the data is spread out, that we are going to talk about are the range, the interquartile range, and the mean absolute deviation. Which measure of central tendency or variability you use will often depend on the way that the data is displayed. So let's look at this data right here. Below is data of the heights of the women's gymnastics team and the women's volleyball team. And we can see that it is displayed in a dot plot. So we have the women's gymnastics team, and then we have their height here in inches, displayed right there. And then we have the women's volleyball team with their height displayed in inches. Okay? At a glance, what do you notice about the mean? So the mean height is like the average height of the women's gymnastic team versus the women's volleyball team. All right, so if I'm just going to glance at this, I'm just going to kind of, without calculating, I'm just going to say about the mean's about right there, and the mean here is about right there. I can just glance at that data and notice that the volleyball team is probably about 10 inches on average, 10, 11 inches taller than the gymnastics team. Now, if I'm just going to look at the spread, again, I'm not going to be doing any calculating. I'm just glancing at this data. And so it says, what do you notice about the variability in height of the women's gymnastics team versus the women's volleyball team? So I'm looking at this spread. If I'm just glancing at the women's gymnastics team and I'm just glancing at the women's volleyball team, I notice that the spread of the data looks similar, meaning this data spread out about the same much as about that data. Okay, now we're actually going to do some calculations. The first question asked me, this is the same data as that was on the previous page, women's gymnastics team, women's volleyball team. It says the mean height of the women's gymnastic team is. So to figure out the mean height of a gymnastics team, I need to sum all the data points and divide by the number of data points. So I'm going to sum 56 plus 58 plus 58 plus 59 plus 59 plus 59 plus 61 plus 62 plus 62 and plus 63. So I'm going to add all of those up and divide by the number of data points, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to divide all of that by 10. So all of this divided by 10, and I get about 59.7 inches. Then I'm going to do the same thing with the women's volleyball team. So here I'm going to do 68 plus 68 plus 69 plus 71 plus 71 plus 71 plus 72 plus 72 plus 73 plus 74. And I'm also going to divide that by 10 because there are 10 data points. And I get that the mean height is about 70.9 inches. What inferences can you make using the above information? And so I cannot say that all women's volleyball teams are about 10 inches taller than the gymnastics team. It's just that in this case, in these women's volleyball team and this gymnastics team, men on the women's volleyball team are on average more than 10 inches taller than members of the women's gymnastics team. So it has to be a little bit of a generalization, but that's what you can infer, that they are about 10 inches taller. Okay, and now it asks me to find the mean absolute deviation of the women's gymnastics team. Now this should be a review, but if you don't remember how to find the mean absolute deviation, let's talk about it. So let's go back up to our dot plot here. We know that the average for the women's gymnastics team is 59.7. We figured that out by adding up all the data points and dividing by the number of data points, which was 10, and we got 59.7. We need to go to each data point and figure out how far is that data point from the mean. So let's start here with 56. So how far is 56 from 59.7? And we can minus 59.7 minus 56, and we're going to get 3.7. How far is 58 from 59.7? Well, that's going to, again, I can subtract if I need to, but that's 1.7. And I'm going to write it twice because there's 2 points there. So each one of those points is 1.7 away from the mean. Okay, how far is 59 right here, these middle points? How far is 59 from the mean? Well, each one of those points is 0.7 away from the mean. Going up here to 61, that's this point. How far is 61 from the mean? And that's going to be 1.3. Again, if you don't know, you can subtract. Looking at these data points, 62. How far is 62 away from 59.7? And that's 2.3. Again, I'm going to write it twice because there's 2 data points. And then I have the number 63. How far is 63 from 59.7? And I get 3.3. So I have found the distance that each point is away from the mean. And now I need to find the average of these points. I'm going to add all of those up and divide by the number of data points. So add them all up, divide by 10, and you should get about 1.84 inches. All right, now we're going to do the same thing with the women's volleyball team. It tells me that the mean is 70.9 inches. So I need to figure out how far is each data point away from the mean. So starting off with these points at 68, well, how far is 68 away from 70.9? And that is 2.9. Again, I'm going to write that twice because there's 2.9s. How far is 69 away from 70.9? And that's going to give me 1.9. And then I'm looking at these data points right here. That's 71. So how far is 70.9 away from 71? And that's 0.1. So 0.1 written 3 times. How far is 72 away from 70.9? And that's 1.1. How far is 73 away from 70.9? And that's 2.1. And 74 would be 3.1. So again, I'm going to sum all of these differences up and divide by the number of points. So that's the average of the distance away from the mean. And if I do that, I'm going to get 1.54 inches. So what inferences can you make using the above information? Well, the heights on each team are spread out almost the same. I mean, there's a slight difference, but I'm not sure that it's enough to make a difference. Okay, let's continue comparing populations. Below is data of wait times to receive ordered food at 2 fast food restaurants. So now our data is displayed in box plots. I have store 1 here and store 2. If I am just at a glance, what is similar about store 1 and store 2, I just noticed. Now remember with box plots, this line here in the middle is the median. And if I'm just glancing, they're pretty similar. They're not that much difference. So I'm going to say that the median of both of them is similar. At a glance, what is different about store 1 and store 2? So again, just glancing, I noticed that this right here, these boxes, which is called the interquartile range, is a lot more spread out than the range of the store 1. Okay, it says a measure of center that you can easily determine from the box plot is, so remember our measures of center that we're going to talk about are the mean, median, and mode. With the box plots, this line here between the boxes, that's the median. And so that's really easy to see on box plots. Then with the measures of variability, we can actually do the range or the interquartile range pretty easily from box plots. The interquartile range might be a little bit more, might give me more data. So I'm going to write that I can easily calculate the interquartile range. So this is the same data as on the previous page. We're actually going to calculate some things. So the first question asks me the median wait time for store 1. So median wait time right here is going to be 2.5 minutes for store 1. Now the median wait time for store 2 looks to be about 2.25 minutes. What inferences can you make using the above information? Well, I'm going to say that the average wait time is about the same for each store. Okay, now it's asking me for the interquartile range for store 1 and the interquartile range for store 2. So let's go back up here to the data. So remember the interquartile range is what's in the middle. So I need to figure out this number, which is 3, and this number right here, which I go down, looks to be about 1.75. So I need to find the difference between 3 and 1.75. So if I minus those, that's going to give me 1.25. So the interquartile range for store 1 is 1.25. Now let's look at the interquartile range for store 2, which would be this number right here. So 4 minus this number right here, which looks to be about what, 0.75. So the difference between those numbers, or if I subtract those numbers, I'm going to get 3.25. So the interquartile range for store 2 is 3.25. Now it asks me, what inferences can you make using the above information? Well, I can say that the variation in wait times for store 2 vary by almost 3 times that of store 1. Okay, everybody, that's it for today. Thank you.